Hello everyone. So you must be surprised to learn that there is some link between classical thermodynamics and quantum mechanics, and so far we have linked entropy and internal energy in terms of the main key factor of this chemical statistics, which is the partition function f. As I have said, that f is the bridge between these two branches of science, classical thermodynamics and quantum mechanics. Okay, so after internal energy and entropy, now we have got so more other functions from thermodynamics, which are known as the work function, Gibbs free energy, enthalpy and pressure, and today we shall also derive a relationship with CV also, and CP would be your task. Okay, so let's start with work function. Okay, so we know the expression of work function from its definition, that it is U minus Ts, and after deriving S and U in terms of F, it has become very easy to establish the relationships for the other thermodynamic terms. In place of S or entropy, we can easily put this value Nk ln F plus U by T from equation number B from the previous lecture. So this value is inserted here in place of S as usual, and then after having multiplied with T, this part becomes Nkt ln F and this part becomes minus U. Okay, so this U would be cancelled by this minus U, and finally what is left? Now minus Nkt ln F. So this is equation C, which expresses A in terms of F. Now pressure. Okay, pressure is a very important state function. If pressure, the expression of pressure is derived, then the expression of volume or temperature can also be derived. Okay, but you have to think which parameter you have to select. Okay, suppose here you have four fundamental thermodynamic equations, isn't it? The expression of dG, the expression of dA, the expression of dH, expression of du as well. So the expression of dG was what? No? It was V dP minus S dt. Okay. Similarly dA minus P dV minus S dt. So all have their expressions. Now from this expression you can have two things. One is pressure, another is entropy. But the value of entropy is already determined. Now how the value of pressure can be determined? So in order to find out the value of pressure, you have to make the temperature constant in order to eliminate this factor. Okay, so if the temperature is made constant, then dt becomes 0 and this part is vanished. So it becomes dA equals to P dV minus P dV, and then dA by dV becomes minus P. But since it is isothermal, then T has to be shown in the suffix of dA by dV expression, and since T is shown in the suffix, that means it's a partial differentiation. That's why the D terms can be written as delta or del, in simple partial differentiation term, del A by del V at constant temperature. So this is minus P, and in the reverse order you can also write P equals to minus del A by del V T. Okay, so you have the expression in equation C, that A equals to minus Nkt ln F. Just you have derived it, so just differentiate this with respect to volume at constant temperature in order to get this value. Okay, the differentiation should be taking place at constant temperature with respect to volume. So what should be the result? The result is very simple. The result is Nkt d ln F by dV. Okay, and that is the expression of pressure P. Okay, and here equation D is obtained. It's very easy. And one question might come to your mind, that why this expression is positive. So you look here, the expression of P is already negative and the expression of A is also negative. So these two negative signs would cancel each other. As a result, this P would have a positive expression. So you get equation number D this way. Now move on to finding out the derivation of G. As you know that G has the thermodynamic expression H minus Ts. Okay, H is the enthalpy, T is temperature, S is entropy, and G gives free energy. And H, by its definition, enthalpy, is actually internal energy plus mechanical energy. That means pressure into volume. So we put this value U plus PV. But simultaneously, we also know that U minus Ts is nothing but work function A. Okay, so A, work function A equals to U minus Ts. So instead of that, we put here A. So the relationship becomes A plus PV. Now we have all the expressions. You have the expression of A, you have the expression of P. So put these values. A has the expression minus NKT ln F, and P has the expression NKT dln F by dt at constant temperature. Okay. So putting all these two values, then finally taking NKT as constant here, and equation E is obtained, which is minus NKT, then within bracket multiplied with ln F plus d ln F by d ln V. Okay, and here one thing is taken, that this V was actually taken to the denominator of this V. Okay, that means dV by V was written as d ln V. So this was the change. This V was vanished due to merging with this del V, and it becomes del ln V, this del ln V. So it should be clear. So this equation E is obtained. Now enthalpy. Okay, finally it was the only thing out of the 5 main functions of thermodynamic. U is obtained, S is obtained, G is obtained, and A is obtained. Now finally H is to determined. So we know by definition enthalpy equal to internal energy plus mechanical energy, pressure volume product. And you have all the expressions U and P. U has the expression NKT square dln F by dt. Okay, and P just you have derived NKT del ln F by del V at constant temperature. So put these values in the expression of enthalpy. So you get NKT square dln F by dt plus NKT d del ln F by del V into V. Then this V can be merged with this del V, so you can write del ln V. Okay, and here from T square you borrow 1T in order to merge with this dt, so you can write here d ln T, and this T square would become T. Okay, so finally you get d ln F by d ln T here, and here del ln F by del ln V at constant temperature here. So NKT can be taken as common, so take this, and then within the bracket you can write this expression. So this is the final expression of H, and thus you get equation number F. Now finally the last expression of today's lecture is heat capacity at constant volume, Cv. So Cv also has the definition del U by del Tv, and just differentiate the expression of U, NKT square dln F by dt. Okay, at constant volume, then you will get the expression of Cv. So in order to do this, just written the del T of NKT square del ln F by del T at constant volume. Okay, then N and K being constant is taken, they are taken out of the bracket. Okay, and then this expression can be written as it is. Okay, this cannot be made, there cannot be made any kind of changes. So this is the expression of Cv. So finally you can find out the value of Cp also in terms of F. So this is the question: find out the expression of heat capacity at constant pressure, that is Cp, in terms of partition function F. And I give you one hint, I won't do this here, you have to do this in your copy. Okay, and you can easily find the relationship as the Cv, expression of Cv is expressed. Okay, so this is the hint. Cv has the thermodynamic expression del H by del T. So just differentiate the expression of H in terms of F with respect to T at constant V. Okay, so and one more thing, that you try to imagine, you try to think, okay, execute your brain in order to find out how the relationship of volume and temperature can be determined with in terms of partition function F. Okay, you just think it, and I hope you can do this. So that's all for this lecture today. Thank you. Have a nice day.